Hello, everybody, and welcome. Today we're going to be talking about the nervous system and neural control of an exercising muscle. So when we think about the nervous system, particularly as we kind of build on with what we talked about in the endocrine system in our previous unit, the nervous system is also going to be really important for control and communication within the body. However, the nervous system is going to function significantly faster in comparison to what we see within the endocrine system. The other thing that's interesting about the nervous system is that it's really a mystery. We've kind of got it figured out in terms of most of the other systems of the body. However, as it relates to the nervous system, there's still a lot of unknowns, which is exciting when we think about how does the system function, how does the system integrate information, and how does that make each of us different in terms of our experiences, in terms of our conscious thoughts and decisions, and how does the physiology of how these neurons work together determine our actions and determine emotion and a lot of those other variables. So still a lot to know, or still a lot to learn in terms of what is going on within this particular system. Our general kind of overview or our functions here, we're going to receive sensory input. So the brain is going to receive some stimuli. And again, that stimuli can be internal stimuli. So we've got sensory receptors inside that are going to tell us if we are thirsty, if we're too hot, if we have a stomach ache, things like that. We're also receiving sensory information from all around us. Those exteroreceptors are going to allow us to perceive the external environment. So what we see, what we smell, what is touching us, all of those factors. We're going to take all that information. We are going to send it to the brain where we process this information and create a plan or response. And then we're going to send signals to the body in order for us to have an appropriate response based on what it was that we were experiencing in that moment. So when we think about how is the system kind of organized, there's a lot of pieces here. So I want to kind of give us an overview, and then we'll kind of get into each of these sections as we move through this lecture. So we have the central nervous system, and the central nervous system is going to be made up of the brain and the spinal cord. And then we have the peripheral nervous system. And I would say these are kind of your two big divisions or your two big branches. And the peripheral nervous system is going to be any nerves outside of the outside of the central nervous system. So anything in the periphery. And two divisions in the peripheral nervous system, we have sensory or afferent neurons, and sensory or afferent neurons are going to ascend or send information up to the brain. And then we also have motor or efferent neurons, and they're going to be descending. So they're going to take the plan from the brain and send it out to wherever we want to have a particular response. We can then subdivide the motor division even further into what we call somatic nervous system. And this is like, think of this as like conscious control. So again, let's say I see my coffee cup and I decide I want to pick it up. Okay, I'm going to send a motor plan from my brain to the somatic nervous system, which is going to allow me to contract the muscles that I need in order to lift up my coffee cup. Okay, so think of those as like conscious control. I decided to do that. Okay, and it's the motor division also has what's called the autonomic system, and think of this system as more automatic in nature. Okay, so the autonomic or automatic nervous system is going to be out of our conscious control. So these are going to be things that happen whether we want them to or not. And these can be sympathetic in nature or parasympathetic in nature. When we have the sympathetic system activated, this is kind of like our, when we're nervous. Okay, so think of this as like our fight or flight response. So if I'm nervous in a game or in an exercise situation, I'm going to start sweating, my heart's going to start racing, and those things are going to happen before I even do anything physical if I've decided that this can be stressful for me when I get into that moment. Okay, parasympathetic system is going to be kind of its opposite. So parasympathetic system is like rest and digest. So normal circumstances, we have parasympathetic control, meaning that we're kind of resting most of the time, and we're under sympathetic control where we feel stressed and we feel ready to go only a little bit of the time. Okay, so again, that kind of gives us an overview of each of these divisions within the nervous system. So again, to kind of get into more details here, and this just shows you in a different kind of view, and you can kind of fill things in as you go here. The central nervous system, again, made up of the brain and the spinal cord, and then the peripheral nervous system is going to include both sensory or afferent neurons that send info up, and motor or efferent neurons, which descend information. Okay, and again, those can be somatic in nature, and that's going to be my conscious control of deciding I want to pick up my coffee cup, or it can be autonomic in nature, which is kind of involuntary. And again, those are going to have kind of an all-encompassing effect on various systems of the body, which we will get into in this unit. Okay, so in order for us to kind of understand how the nervous system works, I want to just zoom in just briefly, and I want to touch the surface here in terms of what's happening at a cellular level. So here you can see a neuron, and a neuron is the basic structural unit of the nervous system. So this is the cell that makes up the nervous system, and it has three major regions. We're going to have a cell body, which you can see here, also known as the soma. We have dendrites, which are these purple projections here. And then we have an axon, which is this yellow section here. Okay, and the next slide, I will give a little bit more detail about what each of these components does. Okay, so here we can see the cell body in the middle, which contains the cell nucleus, and the cell nucleus is like, think of him as like he's like in charge. He's like the brain of the neuron, right? He's the one controlling what's happening. Okay, we also have the dendrites, and the dendrites here are going to allow us to receive information. That information will be summated inside of the cell body or in that cell soma. And if we decide we want to send that information on, we're going to send what's called an action potential down this axon here. Okay. So when we think about structure and function of the nervous system, in order for us to send a message, or in order for us to allow these cells to be excitable, we have to establish an electrical signal for communication. And this is true both in the brain and in the peripheral nervous system. So this is kind of true everywhere in the body for the most part. And so in order for us to excite or generate a response or have a cell be excitable, okay, we need to have a stimuli. And that stimuli is going to be propagated down the axon. So again, we said the axon, if we decide that we want to send a message, we're going to send a signal or an action potential down the axon in order for us to communicate that information to the next guy in line. Yeah. Okay. So in order for us to establish excitability, we need to have something called the resting membrane potential. And again, I just want to just slide over the surface of this so that we have a general understanding of this, but I don't want to spend a whole lot of time here. So essentially, when we say we have a resting membrane potential, we have established an electrochemical gradient inside the cell in comparison to outside the cell. So we have different charges and different concentrations of items. Let's see if I can draw you a little picture. So essentially, inside the cell, it is more negative. So inside the cell has a charge of -70 in comparison to outside the cell. Okay, and we have to maintain this negative membrane potential in order for this cell to be excitable. Okay, so in order for this cell to send a signal, we have to change that charge and reach what's called a threshold in order for us to send a signal to the next cell in line. And these cells are going to work in a unidirectional way. So what does that mean? It means that I'm going to receive from my dendrites, I'm going to send through the axon. Okay, so it's only moving one direction. It's going, like I said, from the dendrites to the cell soma through the axon, and that's how we're going to send a signal. Okay, so -70 millivolts is the charge inside of that cell. And essentially what is causing this negative charge, it has to do with an uneven concentration or separation of these ions in different locations. Okay, so the walls of the cell are what's called selectively permeable. So only certain things can pass through easily. And so basically what we're doing in order to create this potential is keeping more negative things inside and allowing the positive to stay on the outside of the cell. Okay, which is what creates polarization, okay, or a difference in that charge inside versus outside. Okay, so in order for us to send a signal, again, I need to basically change that negative that I have to positive. Okay, so in order for us to send an action potential, which is like your signal, okay, I'm going to take my resting potential, which we said was -70, and I'm going to allow these positive molecules, which are sodium molecules with a positive charge, into the cell, causing the cell to become more positive or depolarized. Okay, this allows me to send an action potential. Then I need that cell to recover through a process called repolarization. And this will allow us to return back to our resting positions or our resting values, okay, and allow us to be prepared to send another signal pretty fast. Because again, remember, the nervous system is freaking fast. Like, we can do things with a great amount of speed, a great amount of power. The only way we can do that is through quick integration of sensory information and quick and synchronized responses of our motor plans through this depolarization process. Okay. In order for us to reach an action potential, again, we said we need an action potential in order for us to truly be able to send that message. Okay. Sometimes we can have a bunch of little graded potentials. Okay. So think of this. This is going to be a really weird analogy, but I think you can all relate to it. Whether you are a guy or a girl, you've probably been in a relationship with somebody. And maybe something is kind of eating at that person or at you, right? And so it's just these little things kind of building up, building up. And none of them are really that major, but they're just little tiny pieces that have kind of made you mad. And then eventually, after several of these little pieces that made you mad, you just kind of blow up, right? So that's kind of how this works. The graded potentials are like little pieces that are changing that charge, but you have to have a bunch of little pieces in order for that to kind of blow up and in order for us to have that action potential occur. That's my best example there. Okay, so we're going to take those graded potentials, those little jabs, and sum them together in order for us to like kind of have that freak out. And again, when you're thinking about this as it relates to relationships, you might be thinking like, well, why did she freak out? This wasn't that big of a deal that I forgot to put the coffee cup away or whatever. And it's like, well, no, it wasn't that you didn't put the coffee cup away. It's the accumulation of you didn't put the coffee cup away, and I'm mad about this, and I'm mad about this, right? So again, it's that accumulation of those graded potentials that will allow us to eventually kind of explode in our anger, maybe, which in this example is that action potential. I kind of like that analogy. I'm going to keep that. Okay. Now, these graded potentials can be good or bad, right? So they can be excitable or inhibitory. Okay. So again, if we're pushing, we're jabbing, jabbing, jabbing towards this kind of this blow up, right? You're probably also doing some good things in there, right? So even though you forgot to put the coffee cup away, you wash the car or whatever. So that gives you kind of a plus versus this minus, right? So again, we can be receiving all this information all the time, and some are good, some are bad. So we still have to decide how to summate that information at the end of the day. So that's what we mean when we say these graded potentials can be excitable or inhibitory. Okay. Again, once we decide to send that action potential, we're going to send it down that axon, and it's going to move in a unidirectional way. So it can only move in one direction once we've reached whatever that graded threshold is. So it can only be excitatory if you decide to send the signal. Okay, a little more about action potentials. They're rapid, substantial depolarization. So again, they're going to be very fast, which is what allows us in sport to be able to do things with a great amount of power and speed and reaction. Okay. And they're going to create a substantial depolarization. So that means that cell is going to change from -70 up to a positive value of approximately 30 millivolts in order for us to experience the signal being sent. Lasts about 1 millisecond. Again, that's nuts when we think about speed and reaction for athletics, right? And some of us are better than others at being able to send this signal really quickly and integrate our responses. Again, a lot of times this will begin as those graded potentials, like we said, that need to summate into an action potential or depolarization. Okay. This just kind of shows you what that looks like from a charge perspective. And this down here shows you what's going on with the ions. Okay, I'm not going to be super concerned with the ion movements because I want to move forward and think about how we can apply this to sport. But I do want to kind of just, again, kind of just breeze over the surface here. So essentially what happens is I have a stimulus. And once that stimulus reaches that threshold level where we're like, yep, we're going to send a signal, we see a rapid increase in the electrical potential, okay, causing a change from -70 to +30. Again, this only takes a millisecond in order for us to have this occur. That's known as depolarization. Okay, then once we've sent that signal, we have to recover. And so we're going to do something called repolarization, which is shown here. And repolarization is when we bring that cell from that positive and we want to head back towards our resting values. And that is the process of repolarization. Generally speaking, we accidentally dip a little bit too low. So we're going to be underneath kind of where our starting point was. And again, that's just going to give us just a little bit, it's called an overshoot, and it just gives us a little bit of a lag time in terms of when we're ready to send another signal. Okay. During that lag time and during the action potential itself, we have what's called an absolute refractory period. Okay, so this is during depolarization and then also shortly after. And this is when a neuron is unable to respond to another stimuli. Okay, so we sent a signal and we cannot send another signal until we're done with this one. Okay, so that's the absolute refractory period. No matter how strong the stimuli is, we cannot send another signal yet. Okay. With a relative refractory period, okay, there's another like short amount of time after the absolute refractory period where if the stimulus is strong enough, we could probably send another action potential, but it's got to be a pretty strong stimulus in order for us to accomplish this. Okay, so I guess a good example of absolute versus relative refractory period. This is probably a little weird, but you know what? Let's get after it. So when we send an action potential, think of this as like flushing the toilet. Okay, so when we flush that toilet, there is a amount of time where no matter how many times I push on that handle, I can't flush it again. Okay, that's your absolute refractory period. Then there's another little period of time where I can flush it and it'll go, but it's not going to be as strong as what it would be if I waited till it was totally recovered. Okay, and that is your relative refractory period. Okay, so again, we can send a signal, but it's not going to be quite as good as what it might be if we kind of waited till we're totally recovered from that first flush. Okay. So again, when we send these action potentials, we are going to propagate this down the axon. Okay, so again, here you can see the dendrites. The dendrites were going to receive information. They were going to sum that information inside of the cell body. If they decide to send the signal, it's going to go down that axon. Okay, now the cool thing here is that we can determine how fast we send the signal based on a few different factors. Okay, so if this axon is larger, it will send a signal faster. By larger, I mean like wider in diameter. So it needs to be like wider. Longer wouldn't be good, but we want it to be wider. Again, think of this as like a hose versus a straw. Okay, I can send a signal really quick down a hose because there's less resistance to overcome versus in a straw, which is going to be more narrow, more resistance. Okay, the other factor that's important and determining how quickly we can send a signal is myelin. And myelin is this like yellow fatty covering over the axon. The more myelin I have, the quicker I can send the signal. And actually, one thing that's I think super interesting when we think about myelin is we don't really develop this until we don't develop a lot of it, I should say, until after we're born. So again, if you've been around kids, particularly young kids, they're super clumsy, they're not fast, they don't have good reaction. And part of that has to do with their ability to send action potentials. Okay. Until I've developed my myelin, I'm not going to be able to send signals quite as fast, which is why their reaction times are significantly slower than what we would see in adolescence or adulthood. Okay. So when we think about how we transmit or send this action potential from one cell to another, we have something called a synapse. And the synapse is like actually a gap, so they're not actually touching each other, but it is the interaction between an axon terminal, which are these little blue portions, and the dendrite of another cell. Okay, so you can see another synapse on this side. So we have the axon terminals in blue of this cell, and they're going to interact with the dendrites of this cell. Okay, then, so again, think of this as like we're going to send a signal from this one to this one to this one. Okay, so again, we're only going to move in one direction for the signaling. So it's only going to go like this way. Okay. Now, as I mentioned, these aren't actually touching each other. That's important to note. And the way in which we are going to signal from this axon terminal to this yellow dendrite has to do with the release of something called a neurotransmitter. And a neurotransmitter is going to help us to send the signal from this neuron down to this neuron. Okay. So again, like I said, there's a gap or a junction between each of these cells, just a small little section where they're not actually touching each other. And again, at this site, we need to release something called a neurotransmitter that's going to allow us to send the signal from one to the next. Okay. So here you can see what it looks like when I have a neuron up here and a muscle down here. Okay, so the neuromuscular junction is the interaction between the neuron and the muscle cell. Okay, and again, this is going to require us to release a neurotransmitter, which you can see over here. And the neurotransmitter that we're going to release from neuron to muscle is known as acetylcholine. Okay, and acetylcholine is going to be this little green stuff in these little packages. And basically, once that action potential reaches here, it's going to cause those little green molecules to float into this gap here. I like using this little pen right now. This is good. So we can put those little green chunks into this little gap. And then those little green chunks, which are acetylcholine, are going to bind to receptors, these little purple things, on the muscle cell. And that's what's going to allow this muscle cell to then be excited based on the signal that was sent down the neuron. Okay. So again, here you can kind of see the relationship. We've got a neuron here, and this neuron is going to interact with all these different muscle cells. Okay, and at each of those locations, you can see we're releasing that acetylcholine into this junction or into this gap. And that's going to allow us to stimulate each of these individual muscle cells in order for us to cause excitation of the muscle itself. Okay, so now we're going to move forward, and we've kind of got a good intro in terms of how we're sending signals. Now we want to kind of take a step back and head up and talk about the central nervous system. We want to kind of explore what's happening with the brain and how do we decide which signals to send when, and how is that kind of all put together in order for us to be able to send those action potentials and cause excitation in a variety of motor settings. So let's get into it. All right, so we have the basic organization of the brain. You have 4 major sections here. So I've got 1, 2, 3, 4 listed on my on my PowerPoint here for some reason. There's only 1, 3, and 1, 4. I don't know how I did that, but let's go with it. Okay, so number 1, I have the cerebrum or cerebral hemisphere, which you can see here. Okay, the cerebral hemisphere is going to be this like tannish area, and we'll talk about each of the branches of that here coming up. Okay, we also have what's known as the diencephalon. Okay, the diencephalon is going to be this like purpley section here. Okay, and we'll talk about each of those components coming up. Next, we have the cerebellum, which is known as like the little brain, and the cerebellum is this like pink section down here. And then lastly, we have the brainstem, and the brainstem is going to be made up of the pons, midbrain, and medulla oblongata. Okay, so we'll talk about kind of this hierarchy and what each of these areas is going to be responsible for as it relates to actions and control from the brain. Okay. So let's start with the cerebrum or the cerebral hemisphere, and we have 5 lobes. Okay. 4 superficial kind of outer lobes. We have a frontal lobe, and the frontal lobe is in charge of like higher order thinking. Okay, so general intellect and motor control. So again, deciding what you want to do, where you really are putting a lot of thought into your actions or into your judgments, that type of stuff will be taken care of in that frontal lobe. The temporal lobe is also where we're going to have what's known as the auditory cortex, and that's going to allow us to receive information from our ears or auditory, and also interpretation here. Okay, so again, we're able to understand language in different languages within the temporal lobe. Parietal lobe is going to be in charge of general sensory input. So it's going to allow us to receive information from all those sensory receptors, whether they're facing out and allowing us to receive, information from what's around us, but also internal sensory receptors as well that are going to tell us about joint position. They're going to tell us about heat. They're going to tell us about pain, all those different factors. And then the occipital lobe is going to be on the posterior side of the head, and this is going to include our visual input or interpretation. Okay. We also have 1 central or deep lobe. Okay, so those are your 4 superficial lobes. We have an insular lobe, which is in charge of emotion and self-perception. And again, think of how different this is, and think of how different this might be from day to day, but also over your lifetime, how has this changed, right? So again, when we think about working with younger athletes in particular, understanding that they don't know how to control their emotions. They maybe don't have a good self-perception, or they don't have a good, what's the word? Like they don't have a clear understanding of their role sometimes, or they're just either they think they're really great and they're not great, or vice versa, right? They are really great, but they have no confidence. So self-perception and reality don't always line up when you're working with younger athletes, when they're not very mature. So again, this is, without getting into a lot of the psychology of it, really, really interesting when we think about how we help our athletes and how we can understand their level of maturity or lack thereof, kind of based on their age, based on their previous experiences. Okay, so here you can kind of see each of those lobes that we just talked about. So again, frontal lobe shown here in the pink, where we're going to make those conscious decisions of, yes, I want to go to practice. Yes, I want to work hard in this workout. No, I want to make this excuse and not go to practice today. Or no, I don't want to do this because it's going to be too challenging, right? Those are all higher order types of things that our athletes are kind of coping with. Okay, parietal lobe again is that sensory information where we're receiving information at all times from our surroundings. Occipital lobe, we're going to be receiving vision and kind of creating plans based on what it is that we see. Temporal lobe, what do we hear and how do we perceive that? So again, you think about hearing words versus truly understanding words. Those are two different things, right? So again, thinking about that and how we truly conceptualize what is being said, and also the tone of how it's being said, right? If I say, you're doing a great job versus you're doing a great job, right? Those mean two different things. And so how are we perceiving the words that are said in the tone that they're said? So again, that's going to occur here at the temporal lobe. Okay, here you can see as it relates to, sorry, why am I?
Something went wrong.
My phone thought I was talking to her. Here we can take a look at the cerebrum as it relates to exercise physiology. And again, we've got this primary motor cortex found in the frontal lobe. So here you can see that here, this kind of this purpley area. And then we also have this primary sensory cortex, which you can see here. Look how conveniently located these are. So that motor cortex is part of the frontal lobe. That sensory cortex is part of the parietal lobe. And they're super close together. So essentially what we're looking at here is that I'm going to receive information in the sensory cortex, and then I'm going to send it over, and then the motor cortex is going to create a response to that. Okay, so again, this will allow us to kind of have conscious control of skeletal muscle movement, right? So again, thinking about body position and responses to what's going on around me, right? So again, if I'm a tennis player and I want to complete my serve, right? I have a motor plan for that. I already have a plan that's kind of automatic, and I know what I need to do to produce the appropriate amount of power in order for me to serve the tennis ball. Okay. However, based on the sensory information that I'm receiving, maybe it's super windy, right? So again, using that information, I can then manipulate or modify that motor plan based on what's going on around me. Okay, so again, this is going to allow us to have that integration of what is our plan and how do I need to modify it based on what's happening around me. The basal ganglia, you can see here in green. Let me get my little pointer here in green. Okay. Or cerebral white matter. These are clusters of cell bodies that are deep in the cerebral cortex, and they'll help to initiate sustained or repetitive movements such as walking, running, posture, muscle tone. So again, thinking about those kind of more automatic types of things or repetitive types of things. Okay, so again, once you have the motor memory or the muscle memory for that particular thing, like running, right? It's in there, right? So this basal ganglia is going to be important for that. Okay. Other skills can become repetitive. So swimming, I wouldn't say is a supernatural repetitive movement, but for a swimmer, it is. It absolutely is. So again, it really depends on the skill level of the athlete, but the idea here is we want that to become a repetitive, sustained movement for that particular type of person. And that's going to allow them to get in the pool, not really think about it, and be able to maintain the muscle tone and body position that they need in order to continue with their swim stroke. Okay, other areas of the brain. So every part of the brain that communicates with the cerebral cortex must relay its information through the thalamus. Okay, so this serves as a major relay station for both sensory impulses and serves as a relay site for communication up to the cerebral cortex. So think of this as like the gateway to get up to the higher order thinking. And this is part of the diencephalon. So this is one of the three components of the diencephalon. So again, the thalamus is going to be really important for integrating that sensory information so that we kind of can start thinking about what it is that I'm going to change. So with the tennis example, right? So again, I kind of have my automatic plan for how to serve the tennis ball. And as I receive this sensory information about it being windy, I can then decide, okay, do I need to hit it harder or less hard now, right? And again, that's going to change as I move to either side of the tennis court, or it's going to change if the wind changes, right? So again, kind of constantly receiving that information through the thalamus so that I can kind of decide what to do. Okay, the hypothalamus is another section of the diencephalon. The third is known as the epithalamus. I can't remember if I included that in this lecture, but if you were curious to see what that third component was of the diencephalon, it's known as the epithalamus. But let's take a look at the hypothalamus. Hypothalamus, hypo means below, so the hypothalamus is going to sit below the thalamus. And the hypothalamus has 8 functions. What the heck's my deal with the numbering here? There should be a number 8 here at the bottom. Let's talk about these functions, okay? Number 1, control of the autonomic nervous system, such as digestive, sweat, salivary glands, and the heart, okay? Number 2, emotional responses. So the limbic system includes pleasure, rage, sex, and fear, right? Really, really interesting to think that pleasure, rage, sex, and fear are all going to be responded to from the same section of your brain, right? So again, think about how these things can sometimes be mixed up or kind of interconnected, and that can be problematic for people, okay? Number 3 is regulation of body temperature. Number 4, thirst and hunger. Number 5, motivational behavior. Okay, so this is super interesting. So motivational behavior, thinking about controlling our behavior that is rewarding or pleasurable, specifically eating and sexual behavior. Okay, so again, we think about how does the hypothalamus play into determining what I do, right? So I'm getting this release of dopamine, which makes me feel good if I eat XYZ thing. Okay, you're going to get this release of dopamine through sexual behaviors as well. Okay, because this fulfills that reward system and it's pleasurable, that makes us want to do it again, right? So again, that would make us want to eat that cake again or participate in the sexual behaviors again, right? Even if it's risky, right? Even if we know that eating cake isn't good for you, we still want to do it because we get that reward. Same thing with the sexual behaviors, right? Even if it's not a safe choice in terms of the partner or the situation, the scenario, whatever it might be, if that's not a safe environment, we're still potentially willing to risk doing it because of the reward that we receive from doing it. And again, it's really interesting to know that this level of reward and this level of pleasure can vary from person to person, right? Which is why some of us are super motivated to eat chocolate cake. And others of us are like, yeah, it's good, but it's not that good, right? So again, the amount of dopamine that you are released, there are some genetic components that will play a role in what we deem as pleasurable, right? And this is another reason, I know I'm going down a tangent and I'm really like trying to not get into sports psych too much. But this is another reason why people are motivated in different ways, right? Some kids will be super motivated if you, say their name at practice and kind of give them a shout out at practice, right? Some of them are super motivated by the potential that their name might be in the newspaper. We might tweet about them or something along those lines. Some kids are more motivated that you might give them a hug or a pat on the back or something. They want that physical type of reward. So it's really interesting to see what motivates kids and what motivates our athletes and how this reward system can be different for each of them. Okay. All right, enough of that. Number 6, sleep-wake cycle. And again, that really falls more into the epithalamus, but epithalamus and hypothalamus are going to play a role together in terms of creating a sleep-wake cycle. In terms of how that relates to sport performance, really, really important. If we can get good quality, consistent sleep for our athletes, that is huge. That is really key for their recovery, and that can certainly help them with their performance. I would say that is hard at the high school level. I would say it's even harder at the collegiate level, just based on societal norms, right? These kids are going to have 8 a.m. class. Sometimes we're going to have practice or a game or something along those lines, and you're out till midnight, or you don't get home till midnight, right? And you're going to have to still do your homework when you get home or whatever, right? And then the social norms for a college athlete, like maybe I'm going to go out on Saturday night and I'm going to go to the bar or whatever, and now I'm not home till 2 a.m. Now I sleep in on Sunday, and now I have to kind of recover from that bad sleep and try to get back in my routine by Monday morning. Okay. Let's see, number 7, endocrine control. So the hypothalamus, as you might remember from our last unit, is going to be really important in terms of releasing several of our hormones. And then lastly, number 8 is formation of our memory, and that's through the hippocampus. And interestingly, when we think about the hippocampus and we think about the storage or formation of memories, the storage or formation of memories isn't always based on reality, which is kind of scary to think about. But we store our memories not based on what truly happened. We store our memories based on the emotion that we associated with that experience. Okay, so let me give you an example, right? Have you ever had an athletic success where you were like, oh, that was amazing, that was awesome? Okay, I bet if you think back about that memory, you don't remember that it freaking hurt. If it was an athletic event and you had to try your physically hardest that you could, it was pretty painful to do that. And so, we don't store the pain because it was a good experience. We have good emotions linked to it. And so therefore we don't store the pain. This is the same thing that happens in childbirth, right? So again, you go into labor and let me tell you, it freaking hurts. It hurts really bad. And I would consider myself like pretty tough. However, because the emotion associated with giving birth and now I have this baby and it's wonderful and you get this adrenaline release and you have these positive emotions associated with that, you don't store the pain, which is why you have a younger brother or a younger sister, right? Is because we don't store that negative, painful portion of the memory because it was good. Now, the reverse is also true, right? If you have a bad experience, I remember one of the first triathlons I did, I had to get an IV because I like overheated and I didn't do good with nutrition and it was 95 degrees and whatever. And in my mind, I thought that race course was the hardest race course. I was climbing mountains and it was just awful and I was never going to do that again. And then about like 6 years later, I decided to go back and do that same race course. And I go back and do that same race course. I'm like, shit, this course isn't even that hard. Like I just stored it as this awful negative thing because I had a negative experience the first time I did it. So it's really interesting when we think about how emotion really dictates how we save these memories. And the reason for that is it's all about survival, right? So again, if I do this thing and it makes me feel good, I want to do it again, right? If I do this thing and it makes me feel bad or I had a bad experience, I don't want to do it again because there's a chance I won't survive in my mind, right? So again, it's really, really interesting to stop and think about that and stop and think about how our perception of that experience impacts what we remember and how we remember it. Okay, that was a very long slide. Let's move on to cerebellum. Cerebellum means little brain, and our little brain is kind of here on the posterior section next to the brainstem. And this is going to store our motor memory. Okay, our motor memory is going to involve coordinated body movements that become automatic in nature. And so we have, imagine like a little filing cabinet with all these different little plans of how to do particular actions. Okay, so let's say I'm a basketball player. I have a motor plan for how to shoot free throws. I'm going to bounce twice. I'm going to spin the ball, get down in my position, and then release. Okay, so again, we're going to have lots of motor plans based on what we do regularly, right? Now, once you have that motor plan, it is very difficult to modify the errors that you have. So for example, if I learned to shoot that free throw with my elbow out because I was not strong enough to get the ball up as a 10-year-old or however old I was when I created this plan, it's going to be really difficult for me to learn to keep that elbow in order for me to kind of improve that technique. So as a coach, kind of keep that in mind when we're working with people. Ideally, we teach them right the first time, but a lot of times they already have bad habits by the time you get to them or they get to you. And so it's a matter of being really patient in terms of trying to continue with repetitions in order for us to kind of fix those motor plans. Okay. So we can also adjust these plans based on information that we're receiving. So we're going to receive information about equilibrium. Okay, we're going to receive this information from our inner ear or our vestibular system. And again, this is going to allow us to understand body positioning. Okay, we're also going to receive information on current movement of limbs, neck, and trunk. And this will come from proprioceptors in the muscles and tendons. Okay, so again, kind of understanding where I am in space and my body position in comparison to this other sensory information that I'm receiving. And then lastly, I'm going to receive information from the cerebral cortex or higher order. Okay, so again, if I did go back to tennis, okay, I used my motor plan and I was trying to compensate for the wind, but maybe I increased my force too much, right? Now I have that information from the cerebral cortex that says like, okay, you need to increase your force a little bit, but not too much in order for us to kind of manage or account for that wind. Okay. The brainstem has 3 different areas here. We have the medulla, which you can see here in green. We have the pons, which you can see here in blue. And we have the midbrain, which you can see here in red. The job of the brainstem is to coordinate skeletal muscle function, maintain our muscle tone. So again, if I'm sitting here in this chair, I need to maintain the contraction of my back, my neck muscles, my hip flexors in order for me to stay comfortable in this body position. Determine states of consciousness, so sleep-wake cycle, and then innervates the face and head with 10 to 12 pairs of cranial nerves. Okay, so a little bit more about the brainstem. We also have something known as the reticular formation, and this is going to coordinate skeletal muscle function and tone and also control cardiovascular and respiratory function. So again, just kind of taking those coordinated plans and putting them into action, particularly as I transition like from rest to exercise. I want these things to occur in an appropriate grade, right? So I want my heart rate to gradually increase. I want my breathing frequency to gradually increase. I want that skeletal muscle activation to kind of gradually increase as I increase the intensity throughout my warm up. Okay, then I also have the analgesia system. And again, this is where we modulate pain. So we've got endorphin release here during exercise, which its job is to kind of block pain and block pain reception. So we're going to be kind of dealing with that in this particular area. Okay, so just a short note, again, we've talked a lot about the brain and some of the different functions occurring within the brain. We also have the spinal cord, and the spinal cord is going to connect the brain to both the cranial and spinal nerves. And those spinal nerves are going to be part of the peripheral nervous system and allow us to directly supply the skeletal muscles with signals. Will also allow us to like supply like our vital organs, like our stomach, our liver, etc., with neural information as well. Okay, we think about the sensory division of the nervous system. We have lots of different types of sensory receptors. So we have mechanoreceptors, and these mechanoreceptors are going to be important for us to understand stretch, pressure, and physical forces. So again, if I'm playing basketball and I'm trying to block somebody out and I can feel where they are behind me while I'm blocking them out, that's going to be through those mechanoreceptors that I receive that information. Okay, we have thermoreceptors as well. The thermoreceptors are going to be responsible for perceiving temperature. And again, those are going to be both internal and on the skin surface. So we know what's going on around us, but we also know what our temperature is internally as well. We have nociceptors, which are pain receptors. And again, interestingly, when we think about pain, we don't know a lot about it. Honestly, it's all about perception. Okay, so again, these nociceptors are going to receive information and send it up to the brain. But how do we coordinate this information? Really varies substantially from person to person, which is why some of our athletes are really tough and some of them are really not tough. And again, if you're working with younger athletes, it is highly likely that they've never done anything painful before. And so in order for them to build this pain tolerance, they have to kind of experience pain in this graded pattern, right? So again, if they've never done anything hard at all, Now we've got to, get them here and then here and then here and then here, right? So again, we're kind of helping them to build that pain tolerance by exposing them to painful situations in a controlled environment in sport and exercise. Okay, photoreceptors are going to receive light or images. And then chemoreceptors are going to be responsible for receiving information about chemical stimuli. So this could be like blood sugar, carbon dioxide levels within the blood are a couple examples. So again, looking at those chemical concentrations in various locations. Okay. We also have joint kinesthetic receptors, and these are going to be allowing us to understand body position, sense joint position changes and movements, and allow us to understand how to manipulate our body based on some of these other sensory pieces that we're receiving. Another particular receptor that we have is known as a muscle spindle, and these are freaking cool. So we've got this receptor located inside the muscle, and basically how this works. So imagine that, let me move this down so you can see a little bit. So imagine that I want to pick up this coffee cup, okay? And again, through my experience, I have an idea of about how much this coffee cup weighs because I've picked up coffee cups in the past, okay? So as I put my hand on the coffee cup, the gravity associated with trying to lift this, okay, the gravity from the force, however much weight this is going to cause the stretching of those muscle spindles in my muscle. Okay, so that's what's going on here. As a result, we're going to send a message, we're going to send an action potential that will cause the contraction of this muscle in response to the stretch on the muscle. Okay, so I put my hand on the cup, it caused stretch on the muscle. As a result, that muscle contracts, and I've got a little bit of tension, enough tension so that I can lift up my cup, right? So now if I've never lifted up a coffee cup, my brain uses kind of past experiences to kind of estimate how much force I need to produce in order to overcome and lift this cup up. Now, certainly we're not always right here, right? Sometimes I might go to grab it and think it's really heavy and I accidentally pull it up high, or I might grab it and think, whoa, that's heavier than I thought. And then I have to put in a little more force in order to make it happen, okay? So again, we can kind of adjust that pressure, that tension, based on how much stretching occurs against those muscle spindles. We also have another sensory receptor or reflex, we could say, that's going to kind of work in opposition to the spindles. And this is going to be located in the tendon of the muscle, okay, or the like the end part of the muscle. And essentially his job is to do the opposite. So we said with muscle spindle, his reaction is going to be to contract the muscle, activated. Okay, with Golgi tendon, his job is to cause that muscle to completely relax. Okay, so how does this work? Let me give you a good example here. So let's say you are doing bench press, or you've got an athlete doing bench press. Have you ever been doing bench press? And I'm trying to do 8 reps, let's say. Reps 1, 2, 3, 4, 5 are all pretty comfortable. Rep 6 is pretty tough, but I can get it. Rep 7 is really, really tough, but I get it. I get to rep 8 and I get to here and I just completely drop the weight. Right? Did I completely lose muscle control or whatever? No, what happened is Golgi tendon said, that's too much force. We don't want to do that. And so as a result, it shuts off that muscle, causes you to drop the weight, and it's a protective mechanism. The Golgi tendon said, that's too much weight. You're going to cause a muscle tear. And so we're going to shut off the muscle. And that is kind of how Golgi tendon organ works. So when we think about the motor division, again, we're going to transmit information from the brain to the periphery. We said that we have autonomic and somatic division. So somatic is going to be like your conscious control, the movements that you decide to do. And autonomic division is going to be more visceral activity. So again, out of our control type of thing. Okay, so again, with autonomic system, we have this fight or flight response, which is the sympathetic nervous system, and this is going to prepare the body for exercise. Okay, so when we have the sympathetic nervous system activated, we're going to see an increase in heart rate, we're going to see an increase in blood pressure, we're going to see an increase in blood flow to the muscles, we're going to see an increase in the diameter of our airways, which is going to allow us to get more air in. We're going to see an increase in metabolic rate, so we're going to be burning more calories or have more calories available through an increase in glucose levels. and free fatty acid levels. And we're also going to increase our mental activity. So we are going to be able to concentrate more. We're going to be kind of locked in and be ready to respond to various stimuli. Okay. The sympathetic nervous system is activated when we sense stress, when we sense danger. Okay. This is activated when we are in exercise because exercise is a stress. Okay. Now, our body doesn't know the difference between a physical stress and a mental stress. Okay. And so we are prepared to handle fight or flight in this scenario because it's kind of an all-encompassing reaction. Okay. So again, imagine that a lion walks into my office right now. I have a few options. I can fight the lion and try to take him down so that I survive, or I can jump out my window and try to run away. Those are the two options. I can fight or flee or fight. Okay. So again, regardless of which of these options I choose, I need to be ready for maximal exercise in order to survive or potentially survive the situation. So again, that's why we're seeing all these kind of all-encompassing changes. As we said, parasympathetic system is going to be rest or digest, and these are going to be the system that is kind of dominant when we're not exercising. So most of the time, so I would say 23 hours a day, you should be in kind of parasympathetic tone or having parasympathetic domination. Okay, so it's going to oppose the sympathetic effects. So we're going to see an increase in digestion, urination, we're going to conserve energy, we're going to decrease heart rate, and we're going to decrease diameter of vessels and airways. Okay, so thinking about how do we integrate this information? So again, sensory input can evoke motor response regardless of point of integration. So again, this can come from various levels. It can come from the spinal cord, lower regions of the brain, or a motor area within the cerebral cortex. So again, this is a complicated system, like we said, and so we can see modifications occurring at a variety of levels. We can also use what's called a reflex arc or reflex activity, known as a motor reflex, where an impulse is integrated at a lower, simpler level. So let's take a look at this. This is an instant pre-programmed response to a given stimulus. And the idea with this is the response to the stimulus is identical each time, and it's very fast. And this occurs before we have conscious awareness of what's going on. So our brain doesn't even get involved here. We just do the thing, and it's kind of automatic. Okay, so how does this work? Let's say I put my finger on something that's hot. Okay, my immediate response is to pull my hand away. And how does that work? I'm going to send that sensory information to the spinal cord. It's going to be integrated there. And then we're going to have the contraction or the pulling back of that muscle through that alpha motor response before that information even reaches our brain that we have received something hot within our hand. Okay, I think that's everything. I hope you have a great day. Please reach out if you do have any questions.